Okay. Hi, everyone. Welcome, and I'm happy to be here at Devoxx France. It's my first one doing a Devoxx here in Paris, and this is a bigger room than I expected. So hopefully this will work well for a whole 3 hours of all of us being together. The subject is up here. Hopefully you're in the right room. And we'll spend 3 hours talking about this. It's surprising how much you can talk about latency and responsiveness and how things are done right, how things are done wrong, how they can be done better. Because we have such a long time today, longer than normal, and by the way, I've done whole day sessions on this subject, so we won't cover everything. One of the things I'm going to do is I'm going to walk through some material in depth. I do want to try and have some audience interaction. Unlike a normal 45-minute session where we need to get through the things and then later ask, I want you guys to ask things in the middle. And because we're such a big room, it's hard for people to hear if you speak. There are microphones at the two ends. I have a couple of microphones here that we can also pass around if people want to discuss and talk. So feel free during this to get up and walk and ask questions even without a prompt in the middle. Okay? We do have a good amount of time here, and I do want this to be interactive. Some of the material I will talk about, some of the things I will say, are a little bit provocative or controversial. And some of that is intentional. So if none of you challenge any of what I say, great. But you should feel comfortable saying, I don't think that's quite right, or in my environment, this is different. Okay? Good. So let's start looking at the subject itself. Actually, before we do that, how many of you have seen any of my online talks or a talk at some other... Oh, wow. Well, good. Well, you might find some of the material here redundant with some other things you've seen. We'll go slower and in more detail. You'll see some pictures that you probably recognize too. But I like to do a polling usually to see how many people have already looked and thought about the subject. So this is a subject I've been talking about for about almost 3 years. And the first title I gave it was this, How Not to Measure Latency. It really started with looking at the common problems we see with how people think of and then measure latency in general. And it's just things we ran into in our experience in with our product and then working with customers. But then this evolved into more than just here are mistakes other people do. And I'm sure you guys all know how to measure latency correctly, but this is just telling you what other people do. But one of the other things I've started doing is I started calling this the oh shit talk. And ever since I've called it the oh shit talk, I've had a very interesting effect happen with large enough audiences where somewhere in the middle of the talk, somebody will actually say, oh shit, loud, So feel free to do that in the right places. Well, any place you feel is right in this talk. It really does look like, yeah, I think we do that. And I think that is very wrong, or something to that effect. I'll point out a couple of natural places to say it. So I'll do just a quick introduction of who I am. I'm Gil Tene. I'm the CTO and one of the co-founders of Azul Systems. At Azul, I've been working on a lot of things for the last more than a decade, building Java virtual machines. And one of the places I've spent a lot of time, and you probably have heard about, is garbage collection. At Azul, we believe we've solved garbage collection. It's a problem that you never have to deal with again. If you're running regular enterprise applications, messaging, human response time, it's just done. If you're running some lower latency applications, like I know some of the people here are, then it's not completely gone, it's just 1,000 times better. And I'm not talking in metaphors, it's 1,000 times better. We did this by thinking differently, taking an opposite approach to how to deal with garbage collection, and that's not what the talk today is about, but there is background here. This is some evidence of me working on garbage collection. And for those of you who have seen my talks, I apologize. I know you've seen this many times before, but it's the only funny picture I have. So this is actually a trash compactor in my kitchen. The job of a trash compactor, we have these, at least in the US, we have them, is it presses the garbage down, makes it dense, and it basically does minor garbage collections so that it delays the full GC to the weekend where I take the bag out to the real trash can, right? It saves me work. Now in this case, the compactor had a bug in it, and it was stuck. There were fragments falling out the back, see? So I had to defragment it. And I thought at the time that would be really funny to take a picture with the actual garbage collection book. The most important thing about this slide is that that picture was taken in 2004. So it tells you how long I've been thinking this is funny. I really do need a new picture, but I need to find something funny to put on it. Anyway, at Azul we make JVMs that help latency behavior. That's how I ran into the subject. I've personally been working in various performance and latency sensitive fields for about 3 decades now, all the way from real-time and hard real-time systems. So I think I've developed an intuition over time for the subject, but really with our products, because they help latency behavior, we basically find that we always end up measuring how latency behaves with our customers, because that's how people evaluate whether or not they need what we do and whether we actually do what we say. So there's almost always some form of testing of latency behavior involved in us. We don't sell measurement tools. I have nothing to sell you in how to measure or explain latency. The reason I care about it is it's in my way. When I need to show behavior, the fact that there are a lot of issues with how behavior is measured comes in my way. And that's what really got me into this subject as far as talking to other people about it. So I've learned a lot about how people do it, how they think about it, and a lot of the wrong things that they do. Some of the right things as well. So let's start with some philosophy, a little bit motivation and philosophy, just higher level thinking of why are we here, what are we trying to understand, what are we trying to even think about. And the main thing that I want to highlight is that when we talk about latency, and by the way, when I say the word latency, I don't mean latency in the queuing theory sense, which has a very specific definition. I mean latency in the scientific engineering sense, the more common sense, meaning latency and response time and reaction time to me are all the same thing in this context. It's the time from event to response to the event, a time from a request to when I see a response to that, a time from a message entering here and leaving there, whatever it is that you're measuring. I'm not talking about necessarily low latency or high latency. I'm not necessarily talking about a trading system or messaging system or a human response system or even a batch system. It's the length of an operation that we're talking about. And when we are measuring this and trying to understand it, what we're really trying to understand is the behavior of that measurement. It's not what the number is, but how the number behaves that we really are spending our time thinking about. Every operation you do will have its own individual latency. And I don't mean a login is longer than some other click. I mean that every click on the exact same thing will have a separate latency for that click. And if you repeat the click many, many, many times, you really want them to all to be the same, but they're not. And when we measure latency, it's really a question of how does that behave when I repeat the same thing many times. So every operation will have its own latency, and we basically measure again and again and again and again. And if we've looked at a system that's running for a while, we may be looking at 1 million different latencies. And what we're really trying to think about is, how does that million behave? What can I say about it? And is that behavior what I want? Is it good? Is it bad? What in it needs to be improved for my purposes? It's the behavior that we're talking about. And yes, everybody wants latency to be fast, and everybody wants to be fast all the time, but it never will be all the time, and fast is a subjective term. So with that in mind, looking at only one metric, like what is the common case latency, is only a tiny piece of information about the behavior. It's usually not a very useful piece of information about the behavior. It's just a good way to understand some of it. But taking a million results and deducing one number from them is usually a way to not understand or not actually apply too much thinking to the behavior. Now, let me put up a common chart that people look at when they monitor things like response time or behavior. I took this from a website for one of I think this is Graphena, plotting some graphite monitoring data. And I know this is small text, I'll explain what you're seeing here. There are multiple lines plotted over roughly a 2-hour period of time. The top red line is the 95th percentile. Below it in orange is the 90th percentile. Then you have the 75, 20, 75, 50, and 25% lines there. This is the behavior measured over a couple of hours. And this is very common for us to see in monitoring systems. So in a monitoring system, you may be looking at 100 different ones that looks like this, little dashboards with a lot of little things. And we're watching some system, or either the entirety of a cluster or a specific node in a cluster, and we're plotting this over time. Now, you look at this, and a few things come to mind. Anybody want to volunteer what seems interesting in this chart? What draws your eye? Yep, there's a spike. Yeah, it's the biggest thing here. It's the thing you tend to look at. And in that spike, what we see is that at some point in time, 1240, the 95th percentile rose dramatically, and then it dropped back down. We can see that at about the same time, if we think about it, the 90th percentile was also pulled up a little. We can also say that the other percentiles were not strongly affected at the same time, so something happened that affected the 95th, a little bit of the 90, but not more than that. So something happened then, right? And that's often the result of showing a chart like this. We look at the chart, there are lots of numbers, so we start thinking about the numbers. We look for patterns, our eyes look for patterns. And whenever a number is shown to us, we try to understand what it means. But think about this, that's the 95th percentile. You know what's not on this chart? The max. Or anything above the 95th percentile. This is the chart you show your boss if you want to show them how good things are without talking about how bad things are. The bad 5% of things are not on this screen. This is a chart that you show to hide problems, not to show problems. If you are monitoring a system and your job is to pay attention when it's bad, not to pay attention when it's good, because you have 100 things to watch, then this is not the chart that you should draw attention to, right? 5% of your things could go badly wrong before anything will show up on this chart. Now, at this point, many people say, yeah, I understand, but if the top parts go bad, I'll probably see the bottom parts move a little bit too. But look at what that's already telling you, right? The top parts can go bad without the bottom parts moving, right? I mean, if we didn't show the 95th percentile, we wouldn't know there was a spike there. Now, I've been showing this chart in a few different places doing workshops, and I did this in Australia recently in December. And one of the people that attended this was texting with one of his colleagues that happened to have a chart like this. This is an actual chart that they sent me after the workshop to include in this, that shows the 95th and the median and some other things of a system. And they were looking at this and saying, okay, look, there's a rise in 95th percentile, something's going on, let's pay attention to it. And because we were talking about this, he, texted back and said, what do the rest of the spectrum look like? So they pulled out to the 99 percentile. This is the same data, okay? And this yellow line over here is that yellow line over there, right? See, there's some behavior in that last 5% that wasn't shown. And it's dramatically different. So for example, over here we have much, much higher behaviors and they're much worse than you think, or they might happen in times where the other behaviors aren't even pulled up, right? And these are orders of magnitude apart, right? So if what you are doing is looking at the good stuff and ignoring the bad stuff, you might spend a lot of time trying to understand behaviors that are drawing your eye but are not the center part of your system. Now, this is the 99th percentile, so that's much better, right? What about that last 1%? Where is that? And what do you think would happen if we plotted it? I don't actually know because they didn't have the data. In this case, the maximum is not on the chart, right? So looking at the spectrum of results is usually, most commonly at looking at the entire spectrum, understanding the behavior across the field. It's okay to say, I don't care about certain things, but it's not okay not to show them at all. Because if you don't show that 99th percentile, your impression of what the system does would be dramatically different. And if you don't show the maximum, it also wouldn't be the same. So let's do a little bit of polling. We have a nice large audience here, and I want to see what you guys care about. I'll start with assuming that you care about the latency of your systems because you came to talk about this subject. So let's assume that's a given. But how many of you have an actual need, an actual reason to care about the worst case in any given hour or in any given day? It's okay not to have a need for that. Many applications don't. So how many of you actually have this need? Raise your hands. I know it's early in the morning. Okay, so I'd say about 20% seem to be there. So let's lower the bar. Not talking about the worst case you see, but what about the 4 nines, the 99.99 percentile? Does this matter to your application, to your business? How many of you have that need to watch that number? Now, this is strange. It has to be at least as many people as watch the worst case, right? Okay. So it's early in the morning, I know. But let's reverse this then. Okay, rather than make it hard and have you choose the hard things and see if you care about them, let's make it easy. How many of you have a need to look at the fastest operation of the day and you just don't care about anything else? We did a million things today. What was the fastest one? 1,000 things today. What's the fastest one? Anybody can think of a business application for that? There is a common one, by the way. It's called benchmarking. That's what we do, right? So if we measure something, we'll measure it again and again and again and again. I'll pick the best one. That's what I'll tell people, right? That's what benchmarking is. Well, we try not to really do that, but spec benchmarking is that, okay? That's what the rules are. Run it as many times as you want. All you have to do is publish one that was real. You don't have to publish the other ones that were much worse randomly, that were also real. But there isn't really that much use for the fastest operation time, right? It might be interesting to know how fast is possible, but it's not really anything interesting about your actual behavior in the system, right? So let's raise the bar from there a little bit. What if we said not the fastest operation, but the good half? How many of you watch the good half and don't care at all about the other half? Like, not I want to know what it is, but that's where my needs end. I just need the good half to be good. The bad half could be terrible. The bad half could, hey, it doesn't even have to finish. How many of you have an application like that? Okay, not that many. It's pretty rare to find these. I'd like to highlight that the median of the latency in your results shows that and nothing else. The only thing a median shows you is what the good half was. It says absolutely nothing about the bad half, the worse half, right? So again, a useful piece of data about the overall behavior, but not a critical piece of data for your application. It's not a primary indicator of anything you care about. We can raise that more and say, what about 90%, you know? And at this point, by the way, there are real applications that maybe at the 90 or 95 or 99 could say, that's good enough. For example, an application where if you try and you win, you make money, and if you lose nothing except for the opportunity to make money. Ad placement in some cases is like that, as long as you're not doing arbitrage or nobody's watching your SLAs. If you're actually just trying to win, there's good stuff to win, there's a lot of supply, you just go and pick whatever it is you want, and every time you pick before other people, you win. Hey, if I'm 99% good, I could improve my business by 1% by doing even better, but I could probably invest in other places to improve my business to 1% rather than aim for perfection. That's a valid way of looking at things where you say, that's a good enough, right? This changes dramatically when that bad thing is not a lost opportunity, but lost business, lost customers, lost money, risk. So for example, if the meaning of not hitting your SLA is damage, is exposure, it's loss, then that loss is amplified dramatically, or that percentile is amplified dramatically. A common example we see is trading. So in trading, most trading done today is a lot more complicated than, look, there's a good price, I'll pick it. It has a lot to do with I'm looking at some opportunity in the market where there's a disparity between this price, and I could arbitrage it or move my positions across them. FX is like that. Most algos actually play those games around volatility. And what you're really doing is saying, hey, if I buy this and sell that, or buy this and sell that, something more complicated, given current market conditions, I could move $100,000 and make $20. But I could do this all day and make a lot of money. Right? So every time I do this, I win $20. But what if the market conditions changed in between your three operations that needed to happen together on the same prices? And at that point, you know, if things took longer than you think, you might be losing a lot more than $20. You might be losing thousands, or maybe more. So the downside of what happens when things are bad is often much higher than the upside of what happens when they're good. If you want a non-trading example, when a customer is browsing an online shopping site and they click and they get a snappy result, that's very happy, that's good. They'll do this a lot all day, right? They might do it hundreds of times and actually buy from you. So every time you click, they get a good behavior and they like you. They click once and they see a long response time. That's what they remember. That's how you lose a customer, right? And the meaning of a bad response time to a person is much, much worse than the meaning of a good response time. They don't care about the average of the good and the bad. They remember the bad. That's what makes them go away. I tried to buy an airline ticket yesterday, and you've probably all have gone through this. You know, you go through the all, choose it and all that, and then you hit that button to say, charge my credit card. And it sits there and spins. And it says, don't press the back button, don't reload, don't close this screen, right? How many minutes am I supposed to sit in front of that thing? And by the way, it took me 5 minutes until I closed the screen because I couldn't wait, right? Now, the effect of that is much worse than the lost transaction. I'm never using that site again. Not that way. I'm not pressing that button again if I don't have 5 minutes to spare. Right? And even if I did, I'm not sure it's going to complete. I'll probably go and call them on the phone and cost them a lot of money if I do this. More likely, I'll go to their competitor and buy from them. So that's the meaning of bad experience. It doesn't matter that the 100 clicks that led me there were good and that this was the 1%. It's that one bad event that matters. Okay, so we care about the behavior in general. This leads me to a subject I like to call wishful thinking. We all have this problem. I have this problem, I know, and I've been talking about this for several years, where we really want latency to have a certain behavior, so we try and imagine its spread and behavior, given some things we learned. And most of them have to do with basic math and statistics. We learned about statistics, we learned about normal and Gaussian distributions, we learned that if we measure a lot of things in the real world, 35 is the same as infinity. And you know, that's how medical research is done. And that numbers all spread around like this and have shapes. And if we just take all the numbers, do the average and the standard deviation, we'll get a feel for the shape, right? Now this is commonly used scientifically when you have large sets of data and you don't know that much about them. The first thing you do is you try and fit them like this and play with them. And people who study these shapes will do more than look at, you know, the average and standard deviation. They'll extract more metrics to see how normal or not normal it is, things like skewness and kurtosis and other metrics that are interesting. And I keep forgetting what they mean. I believe skewness is how far away to one side or another you are. Kurtosis is sort of the pointiness of the chart, if you want. But the reality is different than this, at least for latency. The thinking often goes like this. If I have the average and a few data points to sanity check that, like 90, 99 percentile, I have a feel for the distribution and I can develop some intuition on how things are. And I make some business decisions based on it. Like how many machines I need to deploy in order to run my stuff and keep people happy. Right? Because I got a feel for the curve. Another way to look at this is if I've covered, and I didn't just put this in for you, right? But if I've covered up to the 99 percentile, I'm done. I mean, yeah, there's this other 1% there, but do I really want to invest in perfection? How bad can it really be? Right? I know it's worse than everything I've measured, but how bad can it really be? Now, those are common intuitive ways of thinking. We all do them all the time. We don't want to think about a million different numbers, so we try and summarize them in our head in some way. And let's look at some real data sets and see what happens with them. This is an actual trading system. And it's a mature trading system. It's been worked on for a while. Now, by the way, I'll use this format for charts across multiple things today. You're looking at the x-axis where there's our percentiles, the 90th and the 99th, and maybe some more, and a y-axis that shows latency or response time for that percentile. So for any given percentile, go look up what the latency is. In the y-axis in this specific case is in milliseconds. This is a 50 to 70 microsecond operation, but this could be milliseconds, seconds, hours if you want. The concept is the same. Okay, we're looking at how distribution works. So in this system, we have a really good flat behavior across a very wide spectrum, all the way well past the 99 percentile on a log chart, right? That's a pretty good system. I mean, people can be proud of this system, right? And they've worked on it for years. But what happens if we scroll to the right? Look at some more numbers. Now, obviously, I put this here because there's data there. This is what happens if you actually keep going to the right. Don't stop at the 99 plus something, right? That's an interesting little bump. And that's a little bump because that's what happens if you go further to the right. See that little bump, right? That's what I showed you before. This is an actual distribution across the whole spectrum for an hour of one system. This is 1 hour. Now, the ratio between the high point and the common case point, not the best case, but the 99 percentile case here, is 1,000 to 1. Literally 1,000 to 1. It's 50 milliseconds to 50 microseconds. And this is common to see in the wild when you actually measure the whole percentile curve, right? Whether it's here where we have milliseconds to microseconds, or when you have seconds to milliseconds, common case operations in the milliseconds, but sometimes a 2 or 3 or 5 second glitch. We're talking about 1,000 to 1 ratios. 1,000 to 1 blows away a lot of our intuition about how bad things can be, right? We looked at the 99 percentile. Look, it's 70 microseconds. How bad could this be? Well, 1,000 times as bad as you think. And 1,000 times as bad as you think could have very big business implications. Now, how do we get these shapes? And by the way, these are usually the shapes you will see if you actually measure your system. You'll see these, humps. I think, I'm sorry about the red contrast there. I believe that these shapes are really driven by requirements. That red line over there is the system requirements here. 2 nines of half a millisecond or better, and 4 nines of 5 milliseconds or better. But that's it. That was all that was required. So what happens right after the 4 nines? Anything you want. And anything you want means usually pretty bad things. Because nobody said it's not allowed to happen, so that's where we'll put all the bad stuff. In fact, the way we usually achieve our good behavior is by creating bad behavior at the high percentiles. Now, usually if you show a chart like this to a CEO or a business owner, you will immediately get requirements to cover the entire spectrum. Right? The only reason they're not there is nobody's ever plotted that. Okay, nobody said, they just said, hey, look, I have my 2 nines and 4 nines. That's pretty good, right? Nobody showed the chart saying that also means I'm allowed to do this 1,000 times worse, and you're going to be okay with it, Mr. Customer, right? So once you start plotting these, you start changing what requirements are told to you, which is why I usually like to communicate in these pictures when we show results. Now, there's another interesting thing I find when I look at these, and I look at a lot of these. I've looked at hundreds of them from real systems. I do what I call latency archaeology. I look at a shape and say, I wonder what made that happen. And here's an interesting little point. See the 3 nines there? And the little bend right at the 3 nines? At some point, somebody cared about that number. It's not in the requirements list. But somebody was watching this number. Somebody worked to improve it. And how do I know this? Because right after the 3 nines, it gets worse. It doesn't happen at 99.3 or 90.5. It happens at 3 nines exactly. That's not an accident. And usually if you look at mature systems people have been working on for a while, you will find that these bends happen at full numbers of nines. Engineers made that happen. It didn't happen by accident. It happened because we improved things until we met requirements. And requirements are at full numbers of nines. That's how we evolved to this. That's not how we start. That's not the first thing you see. But after you've improved your system, it's going to look like that. So I rant about this subject a lot, right? You might have seen some of this. Like, that picture is actually one I use in a blog that says, every single thing in that picture is wrong. There's not a single one that is correct. I showed you the 95 percentile being basically a way of saying, look here, don't look there. In addition, there's some really interesting other things in this chart. Most of the charts that you see for latency will show percentiles, and then at the bottom or somewhere else in the legend, they'll have averages of the percentiles. What does the average of a 95 percentile over the last 2 hours tell me? Absolutely nothing. Now, it's, can I get some intuition from it? No. To give you a very simple and immediate understanding for why it's meaningless, think about the maximum. If I had the maximum plotted over this, what use is the average of the maximum over the last 2 hours? The The maximum of the last 2 hours is the maximum of the last 2 hours. I really couldn't care less about whether some seconds had a lower maximum or not, right? And the average of the maximum of the last 2 hours is just a way of making a bad maximum look good. That's true for any percentile. You can't tell anything about some percentile from the average of that percentile. Averaging percentiles is invalid math. They're just not in the domain that could be averaged. If you have 100 different percentiles, can't say anything about the result from averaging them. The only thing you can say from 100 different 95 percentile data points is that the 95 percentile for all of them is no worse than the worst one. That's the only thing you know. Or you also know that it's no better than the best one. But that's about all you know, right? So that's another one that's very wrong. And then the last one, which is more of it's an annoyance in history that we're never going to get rid of with these monitoring systems. How many of you use StatsD or Graphite for data collection? Okay. So you've seen these charts, I'm sure, right? Because this comes out of those. I could tell that this comes from StatsD because of a very simple thing. It's the legend down at the bottom. The names for these lines is not 99th percentile and 95th percentile. It's upper 95, upper 90, upper 75. That's what they're called. That's the name of the data series that StatsD reported into Graphite. What does the upper 95 mean? The upper 95 is the 5th percentile. The upper 5 is the 95th percentile. That's just wrong text. Now, like I said, that's a pet peeve of mine because we all look at these and we understand that's the 95th percentile, not the upper 95. But we're stuck with this label forever because of a bug in the first version of StatsD, where they reversed the meaning of lower 95 and upper 95. We can't fix that anymore because if we fix it, everybody will get very confused. We have millions of people looking at this data now, so we can't change the label. But the label is literally backwards. It's the opposite of, it says it is the opposite of what it says it is, right? Okay, so enough with that kind of rant. Let's go and tear down some common terms. So outliers and averages are words that we use a lot. And we use them to, in the outlier case, say that's rare, outlier. In fact, in basic statistics, they usually teach you to take the data points, throw away the outliers, then do your statistics, right? So outlier is the thing to ignore. That's actually what we are trying to do when we say that word. And then averages are usually the thing that makes us think a lot of stuff is like that. Yeah, there are other things around, but the average kind of gives me a feel where most things are, right? So here's a data set to show you that both of these terms are very, very bad ways of thinking about latency and response time. This is an actual data set. The 99 percentile is that flat green line at the bottom. It's 60 microseconds. The mean is more than 3 times that number. That's not rare, by the way. Probably 1 in 10 data sets I look at has a mean that is higher than the 90th or the 99th percentile. Even though that's not intuitive, most people think the mean will be close to the median. The mean is often very, very high, much higher than the high percentiles. The other thing is that red line over there, that's the max in any 1 second during that time. And if we ignored the max and stopped measuring at the 99th percentile, calling them outliers would be simply a way of saying, ignore the actual signal that I have to look at. Like, let's look at the good stuff, not the bad stuff. But I'm not just talking about rare. These are not rare. These happen all the time. Almost every second has a big one in it. So throwing them away is throwing away real data about real behavior. Now, so outliers, I like to think about them as tails or high percentiles, something like that, rather than the things to throw away. But let's think about that average. In this data set, there was no data anywhere near the 210 microsecond level. It's the least representative number you have. 99% of data points were below 60. And the rest of them were way up there. There was nothing in 200 microseconds. Zero. It never happened. So if you take the average and think, oh, I think a lot of stuff will be around that, very often you'll be looking at an average that has no data around it. Not at all, because the data is here and there and you're looking in the middle. It's a very common thing to see in actual latency and response time distributions, and that's because there are multiple modes to the system, and the average kind of hides that and spreads them around. Last one to take away is standard deviation. That pink line over there is the same data line I showed you before. It's 1 hour of a run. That's the mean and the standard deviation for that specific data run. And with the that's the actual computed mean and standard deviation. I think there's several million points in this data. And in this data, we have a 99.999%, a 5 nines number, that's 38 plus milliseconds. Now, that's 184 standard deviations away from the mean. And this is a real-world data set. Right? Now, there's nothing wrong with the measurement. There's nothing wrong with the math. This is just what the numbers are. Okay? If we look at basic statistics, normal distributions are supposed to have the 5 nines within 4.5 sigma. If we want to be generous and say, look, it's not quite normal, make it 5, 6, 7 sigma. In a normal distribution, 7 sigma is supposed to cover 9 nines. But let's be nice to it. But 184 sigma is a little much. Right? It'll take billions of years for that number to be possible in that data set if it were normal. Now, there's nothing wrong with any of this. It just means that this is not a normal distribution and that standard deviation is a meaningless number for this data set. Unfortunately, that's the case for every latency and response time distribution you will ever get your hands on. They are not normal distributions. I've yet to see one that is. Idle Linux systems have non-normal distribution when they're doing absolutely nothing. So when you're actually doing stuff, it takes a lot more. Now, what this means is that just like that nice chart that I showed you at the beginning that wasted 2 or 3 minutes of our time looking at a nice spike and trying to understand what the averages mean, putting the standard deviation number next to any latency measurement is just a way of wasting people's time with meaningless information instead of actually highlighting the useful information. And I am telling you that the standard deviation is utterly and absolutely meaningless. At best, it's just noise, but what it actually does is make you think wrong things. It makes you believe wrong things. If I showed you that standard deviation, it would make you think that this data set is somehow contained within a close range of 60 microseconds, or at least milliseconds, but it's not. Now, the 99th percentile. Yes, there are many systems where we could look at a 99th percentile and say that's enough, that's okay. But you have to remember that when we look at systems, there's cumulative effects. For example, if we take a web page, a single web page that I click on and view, and ask, what is my chance of seeing the 99th percentile of something? That depends on what the something is. So for example, if I'm doing a search, what's my chance of seeing the 99th percentile of one search node? Well, that kind of depends on how many search nodes I employ in my one search, right? Often when I do search, it goes to 100 different nodes. Then I'll wait for the last one to come back, right? Or what about a key value store? Or a database engine? Or a CDN thing where I get contents from? Now, each one of these things tends to use latency characterization as a way of describing its behavior. So we might measure how quickly Lucene answers a search with percentiles, or how quickly MySQL or Cassandra or Memcache respond to a query. Or maybe how quickly my edge content thing that I paid a lot of money for so that all of you will get nice pictures from me without carrying it on my site will respond, right? And each one of those tends to stop reporting at the 99th percentile, or maybe in the 99.9 percentile. How many of you have websites or things that use, say, Akamai? Akamai is a great content delivery network. They deliver lots and lots of edge content. But I would ask you to see if they will give you more than their 99th percentile numbers for their CDN. They report those. But it's really, really hard to find what happens beyond those, okay? Now, what is the chance of me, with one web page look, hitting those 99 percentiles? Is it 1%? Or is it slightly higher? And cumulative means, well, we get 99 times 99 times 99, and the likelihood starts increasing. So here are some stats that I collected looking at some common websites. This is the front page of each of those websites. And what I did is all I did is one click to look at the website, and I measured how many different HTTP requests, you could do that easily with a browser, were involved in getting content for completing that picture, that site. And those are the numbers over there. Now, on the right, you have the math that shows what the chance of seeing the 99 percentile is, right? The chance is 1 minus 0.99 to the power of how many things there are. Now, I don't care if the thing is a key value store that ends up serving it, or a CDN, or an HTTP server. I'm getting 100 things. Each one of them has a 99 percentile. The cumulative chance of me seeing one of those, or what they are, would be that. And as you can see, the chance of a human seeing the 99th percentile in a single interaction is extremely high. I'm not talking about a session. I'm not talking about a day. I'm talking about one web page. And if you multiply that by the 5 minutes I spend on the site, or the day that I spent looking at Facebook, which I sometimes do, the numbers are really, really high. The chances that more than half your users are experiencing the 99 percentile are very, very high. And okay, that's the 99 percentile, which you now understand is basically the common case. If you change this math to, say, the 99.99 percentile, you'll find that the chances of a person seeing that with one web page on most of these is more than 2%. More than 1 in 50 pages are going to experience your 4 nines on something that is serving those web content, individual content things. So if you want to know what, 1 in 50 people experience out of your CDN, you're supposed to ask your CDN what their 4 nines are, not what their 2 nines are. What their 2 nines are is what everybody's going to see all the time. It's not the good stuff, it's the common case. Okay, so enough tearing this down. I'm going to move to some other intuition parts, but I'd like to see if there are any questions or challenges to this so far. This is the first long session of the day. You're going to have another one in the afternoon, I assume. But come on, there's got to be some question or some interesting thing somebody wants to say at this point. Nobody wants to disagree with anything?
Could you please repeat how you did the experiment? So you had, for Amazon, 190 requests, and then what? You had the distribution of the requests and just
So the question was to explain how I did the experiment. Amazon here, for example, shows 190 requests. What did I do? I simply went to Amazon.com and opened that little window in the web browser that lets me see the operations running by, and counted how many there were before it went quiet. Right? Before the web page completed and went quiet, there were 190 different requests sent to something. Not the same thing. It went and got 190 different things.
I think that if we have 190 requests, then the probability of seeing the 99% is basically 80%.
Yeah. If we take all the things we talked to and did the 99 percentile across all of them, right? This is not the good or the bad. Just take everything we talked to. If it's the same one I do 190 from, then obviously it's from that. But if you get some of them from a CDN, some from a key value store, some from a web server here and there, just take all that data and take the 99% of that.
Basically, that's the chance of us getting a 99 percentile on one request and not on a full page.
Yeah, on one request of one thing. Now, obviously, these are very heterogeneous requests. So you probably need to do the 99 percentile of that one times the 99 percentile of that one times the 99 percentile of that one, right? But for example, when you have that many requests, many of them are images, and they come from CDN, so that most likely is the 99 percentile of a CDN. In the lower count cases like Google, that 31 there, that's the very quiet Google screen, the one that doesn't have a lot of junk in it. That's 31 requests. Now, that math assumes that all 190 was sent at the same time, right? And I'm just waiting for the last one to come in. That's a very optimistic assumption, right? Because most often I'm going to request one thing, and then it'll tell me where to get the other things and what to even ask for. So there's a lot of serialization in this that is not in this math. This is an optimistic assumption. If you take any serialization into account, meaning it's 190 requests that are done where the shortest thing will be 7 round trips, then you're starting to see much bigger numbers as well. Okay. So let's move to some other intuition that we want to tear down a little bit. This is a classic look at response time behavior. Classic meaning this image is almost 50 years old. This is from an IBM Kix server document that explains what user response time would look like under load. So we tend to think along those lines. This represents a very strong intuition that we have that as load increases, things go bad, which is not wrong. I mean, as load increases, things will go bad. But that shape also drives a lot of our thinking about what proper capacity planning is and what waste looks like and what controls latency. So there are a couple things about this that are very important to stop doing. The first one is whenever you plot something on the x-axis against something you call response time or latency, the first question to ask is, what do you mean by response time or latency? I have 1 million results today. Which one do you want? Right? Now, if we're going to summarize it, how are we going to summarize it? Is it the average? Is it the maximum? Is it some other percentile? Which one are we plotting? Because depending on the answer to that question, the shape of this chart will be completely different. I've shown you how big the difference is between a median and a maximum, 1,000x in more normal data sets. So the shape of this will be very different. And usually the higher percentiles will collapse at lower load for obvious reasons. But the other and more important issue with this chart is that it drives an intuition that load has something to do with latency. That load is somehow a dominant thing that causes response time and latency. And that's wrong. Load interacts with latency only when you start queuing up, only when you fall behind, only when you can't handle the load. Until that point, load is not what causes latency to behave in any way. And your job is usually to make your system stay away from that point. So yes, when you load it too much, things will wait in line. If a spike happens, there's nothing you could do. Things will wait in line. But if you're doing one thing a second, that doesn't mean latency is going to behave well or it's going to be constant. Latency is not a function of load. Only to a very small degree is it controlled by load. Let's look at a common set of results you might see if you actually experiment with this. And people experiment with it all the time. A common load test, which by the way I don't believe is a good methodology, but it's commonly done, is to take a system and change the load on it and see what the response time looks like. under different loads. The reason I don't like this kind of test is because it tends not to hold a steady state long enough to see what latency actually behaves like. People just add another user and another user and another user. They run 30-minute tests going from 0 to 3,000 users, and they say something about the results. But they didn't look at how the system will behave if it was holding 1,000 users for 10 minutes. Right? Because it takes long to do that. There's an assumption that if I measured a few seconds at a load, I've seen the behavior at that load. And that assumption is based on that thing that says latency is a function of load. That's why we even measure this. So let's look at what we're seeing here. This light blue line is the load. We're growing it from low to high. This spiky black line is the response time that we measured. By the way, I just took this from the web, looking for response time charts. I didn't do this measurement. I actually don't know what the system does. I just know that they varied load and they measured response time in some way. Notice these things. That's the main signal here. If you're trying to understand latency behavior, clearly something bad happened to latency at those points. That's where people are going to call to complain. Response time is bad. If you ask them how is the system doing, they're not going to give you credit for the low points. They're going to say, look, during this period of time you had a few bad things happen. Now those bad things are not happening at high load. In fact, you have points here with a very high response time that it's 10 times higher than response time at a much higher load. And the main thing here is that response time here clearly doesn't follow load. It's not a function of the load. It's dominated by something else. Now, if you do look at this a little more, you probably see that the bottom of this line does seem to follow the load. That is common. Common case often is kind of driven by load. But the bad behaviors aren't. Now, how frequently they might be or how deep they might be sometimes is, but this is not a system that's saturated badly at high load because we can clearly see that even at low load it gets some big spikes. Now, I call these things hiccups. And they happen for all kinds of reasons. We're not going to talk about all of them here. We often call this noise. Noise is simply a way of saying, I don't know what it is. We can then try and figure out where the noise comes from, and then we have a name for it, right? I find that very often spikes of this kind are a result not of a long operation where the logic takes a long time, but of paying for something that we've been accumulating as a debt that we need to pay. And this happens at every level of computer systems. So take a fairly low level, like I've had this CPU all to myself for the last 10 milliseconds and I've been running really nice fast operations on it. Now it's somebody else's turn. So I don't get to do anything for the next 10 milliseconds. It's not that an operation took a long time, it's I just don't have CPU now because I've used all of it. Right? I don't deserve all of it. I'm sharing with another neighbor. If you're running on Amazon, that's what's happening to you. Unless you have a dedicated box with some strong SLA, hey, sometimes you get the CPU, sometimes somebody else gets the CPU. What do you think it means when they tell you this is how many compute units you get? If you use more than that, then you'll slow down in a little while. And that's, by the way, true if you run on your own computers and you have a neighbor. It's not Amazon's fault. It's just that's what time sharing means. So that's one way at a low level. Maybe my operations are logging or journaling, and every once in a while I need to flush that. That might take a while, and then everything will run fast again. Maybe I need to garbage collect. Maybe I need to re-index my database. Maybe I need to compact my Cassandra things, right? Any of those things are usually an accumulation of things that I simply didn't spend time on yet, and I got results before, but I do have to deal with them before I do some operations in the future, and therefore I slow down or stall, showing a very high response time. They're a result of how much work I did so far, not of how fast I do things. It's not a result of load, it's a result of work. Load is work over time. This is not load. Do enough operations and you will have to take one of these stalls, right? So which ones these are, I don't know, but they happen all the time. And hiccups, these big spikes, are usually strongly multimodal. And what I mean by multimodal is they don't look anything like a normal distribution, and they are a move from one mode to another mode of behavior. There's usually a fast good mode. That's the common case. That's the median 90th percentile, often all the way to the 99th and above. I showed you how nice flat things are when they're mature, right? That's what the engineers spent most of their time optimizing. Then you have the bad modes and the worst modes. And how many modes depend on your system and its behavior. But there are usually 3, 4 of them, if you actually plot them. If you have 100 of them, it starts kind of mushing together and it's hard to tell what they are. But usually you can tell if you look at them. Now what can you do about this? The common thing people do about this is this. This is very effective. It's very natural. We all tend to do it. And what's the best way to achieve that? It's to measure average and standard deviation. Now let's be very clear on what's going on when you do that. You had 1 million good results. You measured every latency you had. But it's really hard to think about this, and certainly hard to talk to my colleague about 1 million data points. I need to tell them something. So let's summarize them. I'll take the 1 million data points, I'll extract 2 numbers from them, an average and a standard deviation. I'll throw away the 1 million. And from now on, every time somebody asks me a question, I'll look at the standard deviation and the average and answer based on that. For example, if somebody said, what's my 99th percentile? I'll say, well, the average is here and 3 standard deviations from the average is where the 99th percentile is supposed to fall, so that must be where it is. That's my 99th percentile. You'd be surprised at how often that's the answer I get when I ask somebody about their 99th percentile. It's projected, it's not from the data. That is wishful thinking, by definition. You had the data, but you threw it away and instead you wished it looked like this. This is a very common thing. It is always, always wrong. And remember when I told you don't write the standard deviation numbers down next to your data? I report a lot of these data sets, and I do report at the bottom of them the average and the standard deviation and the maximum. And you'll see maybe in some of these examples of that. So people often ask me, you say all this stuff and then you write down the standard deviation. The reason I do that is to show you how wrong it is. Because if you show the max and the standard deviation and the average, and the max is more than, say, 7 standard deviations from the average, you know the standard deviation is wrong. And I look at a lot of data sets, and it's extremely rare for me to see a data set where the maximum is not a lot more than 7 standard deviations away from the mean. So, yeah. Okay, so this is always wrong. What can you do better? Start looking at the spectrum as a whole. Plot the entire percentile range, not just 1 or 2 things, and look at it, against, say, requirements. This is your data. This is a real system. It's not an artificial data set. Real systems tend to look like that. They have these nice, smooth, multiple modes. It's a 3-mode system. It's got a common case, it's got a bad mode, and it's got a worse mode. The common case is fast, but then a couple bad things happen. And that is what a requirement line looks like. This is a telco system, so the requirement line was 99.5% for some level and then 100% for the other. Why 99.5, I don't know, but that was the requirement line for this system. Now the nice thing in looking at data this way is that you could see whether or not you meet requirements, and if you don't meet them, you could see where you need to spend your time. Right? So if this blue line crosses the yellow line from the bottom, crossing up, that's where it broke. It was good up to that point, but it broke there. So it's acceptable behavior all the way here, but that's not acceptable. So the system fails whatever requirements you had. And looking at this picture can save you weeks and months of work. I see a lot of wasted time in people trying to improve systems before they looked at a picture like this. So think about this. You took a system and there were some requirements and you sent it for testing and the test said you failed. So they go back to you and they say, look, your system's not good enough, make it better so it'll pass. And if you don't actually document what exactly happened and where the failures happen and what requirements aren't being met, what do you think engineers are going to do? It's the common thing people do when they're told, hey, the system isn't good enough, make it better. Well, they take out their profilers and they find what code can be improved. They look for the hot code where you spend most of your energy and time, figure out what loops to make faster, what work to not do, make it faster. The assumption is making it faster will help pass requirements. But look at this picture. A profiler will improve the common case. The common case is passing by more than 10x. Why would you spend time making that better? In fact, spending time there is not just a waste of time. It's most likely going to make the worst case worse. So here's a little revelation for you. Optimization is usually about making the common case better at the expense of the outliers, of the rare things. It's a trade-off. What every compiler does and when it optimizes, it says, this happens 1,000 times, this happens once. So if I make this 1% better and make this 10 times worse, I win. Why? Because on the average, I will go faster. Optimizing this system and making it better, faster at the common case will most likely move you worse or in the reverse direction of what you're supposed to do. Now, yes, sometimes making things faster makes everything faster. Don't get me wrong. Yeah, sometimes that helps. But what you're supposed to ask yourself is, what happens once in 10,000 times that is bad enough to fail? And how can I make that thing not happen? Was there a question here? I think somebody raised their hand. No. So let me give you a specific example of an optimization you might or might not know about that has this kind of behavior. I know that's not what caused this. Mostly because if it happened, it would be bigger and worse than this. How many of you know what bias locking is? A handful of people. Okay, so let me explain what it is. How many of you run on Java virtual machines? Okay, a lot of people. Good. So, good. This is relevant to you, and it's not just for JVMs, but most JVMs actually employ this optimization. Bias locking is a brilliant optimization. It's a really cool observation. It's based on a really cool observation. So JVMs for the last more than 15 years have already been optimizing for contention being rare. So synchronized blocks and locks tend to say, hey, I think I'm going to win here. I think nobody's actually contending with me. I'll do a fast atomic operation and only deal with the more expensive parts if that fails. This goes all the way down to they don't even create the structure needed to block. It's done using a single atomic word on a header, and you just do a CAS to grab it, a CAS to release it. Nobody ever contends with you. You go fast. It's only if some actual contention happened that you have to actually do a lot more expensive work. And JVMs have learned to optimize for this because so much Java code is thread safe that most of the code is running thread safe, single-threaded. Most data structures that are thread safe are actually never used by more than one thread, so the contention is very low. Even if they are used by more than one thread, the contention still tends to be fairly low. So this is a big win. That's not what bias locking is. That's a background. Bias locking goes one step further than that. It says, what if I could avoid using atomic operations for my lock? Because atomic operations take more cycles. They have ordering requirements. They're fairly expensive. So if I can avoid using them altogether, I'll get even faster locks, and I could even apply some interesting optimization to the lock. But to do that, I have to make a really bold assumption. I need to assume that not only is contention low, but my thread is the only thread that will ever interact with this lock. That's what biasing means. It biases the lock to the thread. Decides that the thread that grabbed the lock will own it. Nobody will ever take it away from it, or we hope so. Now the way this works is it literally makes the thread own the lock, and the thread doesn't release the lock, even when you say the lock is over. When it grabs it, it belongs to it, so it can grab it, release it without doing any atomic operations because it just owns the lock all the time. And that works really well because it makes the locking faster in the common case by another several percent. It makes benchmarks like SpecJBB improve by several percent. That's a very big win for compilers and locks. But, and there's a but, in the rare case where the lock you decided to bias to your thread actually does have contention, some other thread actually tries to grab it, we need to revert this optimization. And reverting the optimization is much more expensive than simply making a monitor and doing some bigger things and interacting with your CADs, because you're not doing atomic operations and it's not safe to interact with you. The reason bias locking is possible is because JVMs are able to stop threads and manipulate their stacks. So the way bias locking works to debias the lock, take it away from an owner thread, is you say, stall that thread at a safe point in the code where I can do surgery on its stack. Once it's stalled, I want to go change this lock from being owned by that thread to being a regular lock I can actually grab. In order to do that, I need to change the state of the stack of the thread that owns it, because it has things in there that relate to that are wrong if I do that. So we'll go do surgery on a thread. To do that, we have to stop the thread, right? It's called a safe point. We bring the thread to a safe point, and then we do some operations on it. A slight unfortunate thing is that in most JVMs, bringing one thread to a safe point is not something the JV knows how to do. It does, however, know how to bring all threads to a safe point. So if I optimize the thread, a single lock, to be biased, and then I need to debias it, I have to stall the entire JVM, wait for all the threads to come to a safe point. Don't do anything until they're all back. Now let's go do the surgery, now let them go. It's usually a multi-millisecond operation. Often a multi-millisecond operation. Depends on other noises in your system. Or at least a big fraction of a millisecond. And that's one lock. What if you made a mistake on 1,000 different locks? Now, JVMs will learn about this. They'll see what makes a lot of mistakes, and then it'll say, you know what, that class we're losing a lot on. And let's not do that anymore for that class. In fact, the JVM has a really cool optimization to deal with this problem. It doesn't start biasing until several minutes after you start running. And the reason for that is often during startup you produce a lot of things that the producer actually initialized with locks, and then somebody else will deal with them, and every one of those will get debiased at a high cost if you actually started biasing early. That helps things like SpecJBB, because SpecJBB actually produces all of its objects in the first minute or so, and then goes and benchmarks them with other threads. So if you actually biased early, you would have terrible results. It doesn't really help producer-consumer relationships in the real world. So, it'll take them a while to learn. Now, why did I dive into this? It's a good, common example of how optimization that is a big win to a benchmark and to a common case and to even the 99 percentile will end up moving the bad behavior to be dramatically worse. Right? It'll do the opposite of what you're supposed to if you're looking at improving your failure on high percentiles. Okay, so that was a little bit of what's wrong and in thinking about outliers and the rest, and how to try and think about the entire spectrum and what you need to do there. But latency doesn't live alone, right? I said that latency is something that is driven by a lot of different behaviors like accumulated work, but load does have something to do with latency, because if a lot of things arrive at the same time, you will have to deal with queuing. And when we measure the behavior of systems, if we measure them purely for constant arrival rate, we're being a little optimistic. This is a chart from LMAX, actually. I did a presentation with them a month ago in London about their use of our stuff. And what this chart actually depicts is, this is an average across an entire day of when during a second things arrive. So this is the volume per millisecond within a second, average across an entire day. The left side is 0, the right side is 1,000. And what you can see is sort of, 4 times per second, there's a big spike. It's 0, 250, 500, 750, right? 4 times per second, traffic is high, much higher than the rest of the second. If I looked at this and just said how many things per second are happening, that's what that red line is. That's the rate per second. But you can see that within a second, things happen much faster than the rate per second. And this is an average. This is across all seconds in a day. A given second could be much, much higher than that. The peak load times will be dramatically higher than this average, right? This is a normal thing when you look at markets or at execution venues, because some other external things often ticks. I actually don't remember what this is. Maybe it's Reuters or something else. But something comes in with new information 4 times a second at constant times in the second, so things react to that information, so you have high load for a few milliseconds. But that's a lot of requests coming in. So at that point, it does start to matter how fast we can draw them down, how many of them per second we can handle. Because it's no longer about what it takes to do one of them, it's I have 100 to do and they all arrived at the same time. How long it takes the number 100 to complete will probably be determined by how fast I can draw down on the queue, right? So keep in mind that things per second are not a very good way to look at throughput that you need to keep up with. You often need to be able to keep up with throughput that's an order magnitude or 2 that in order to survive any kind of inter-second peak or intra-second peak, sorry. So if I built a system that can handle that average very well, it would fail 4 times a second, right? Because the real world will hit it, or actually a lot more than 4 times. You can see all those spikes that are higher. Okay, so it's not constant behavior. It's also not stochastic. Now, I've been looking at a lot of latency chart. I could certainly tell you it's not normal distribution or stochastic. I haven't looked at enough arrival rate charts to get a good intuition for them. I can't quite say what the behaviors tend to be, whether they're multimodal or spiky, whether there's a pattern in time or not. This is just one system. But it is very clear that they don't have a normal distribution. They're not stochastic. You don't model this with a standard deviation. They tend to come in spikes. So keep that in mind when you're thinking of how much you can handle or how much you need to handle. So let's look back at that chart, right? The correct part of this chart is that if you overload the system, meaning you ask it to do more than it can do per second, things will start waiting in line, and you will start seeing latency dominated by queuing, not by noise, right? And when you look at that, the common question to ask, say in capacity planning, is, okay, how many of these systems do I need to handle what kind of load? Can I run all of Google on my laptop? And probably the answer is no. So how many laptops do I need? Or bigger than laptop things. And we need to come up with a methodology to answer that question. Now, if you ask some vendor that's trying to push you their product, how many things per second can your box do, they're going to give you the benchmark number. And the benchmark number shows that this box actually moved this many things per second, right? I mean, that load was handled. You didn't ask them whether it was handled happily, whether people complained or not. It's, can you move that many things per second through the system? And they'll say, look, I can move that many widgets per second through a system. If you add the users of the system, by definition, that's where they say you failed. Why by definition? That's where you went from acceptable to unacceptable. I'm assuming unacceptable means fail. Right? So that's the point where that happened. Now, if you ask the capacity planners, most of the engineers, the people who need to come in on a weekend if something goes wrong, they'll say we need to be here or far to the left of that point. I don't want to be anywhere near those points. If you want to ask me how much this can handle, that's how much, right? And the factor that they'll choose will vary based on what they see in this chart. Remember, depending on which response time you plotted, the chart will be different. So they'll pick that point because it looks like the bad things only happen here. Remember, if you actually showed them, say, the 99th percentile, maybe they started happening well before that. Their choice of what capacity they will say they need will be determined by what you show in these charts. So if you show the average, there'll be capacity planning for the average behavior rather than for the peak behavior during the second or the day or whatever it is. And if they do that, then every day they're going to fail. And somebody will say, you planned wrong, right? Which is why they pad. The reaction to this is usually, yeah, I know if I actually follow these numbers, it'll all be wrong, so I need 5x. That takes care of mistakes often, but you don't really know. Now, there's an important point in throughput to watch for, to actually measure. Something you can actually design experiments to determine. And that is the carrying capacity of the system within requirements. It's the sustainable throughput level. The sustainable throughput level is not how many things per second this can move. It's how many things per second this can move while meeting requirements. So I define it here. So it's the throughput you can achieve while maintaining service levels. And service levels is not just latency requirements. It's not just what the common case is and the max is and whatever percentiles are that you state. Service levels include things like correctness. How many times does 1 + 1 need to be 2? How often is it okay for that not to be the case? How many times is it okay to not answer? How many times is it okay for me to lose a message? Those are all examples of service levels, right? They don't just have to do with latency. Does it need to be blue or can it sometimes be red? So how fast can you run so that whatever requirements you've set are all being met? And the reason that's important is knowing how fast you can run where you don't meet requirements is not a useful metric. You don't need to spend a lot of time figuring that out. This is not a worthwhile experiment to repeat many times a day. I could take a red car and I can answer how fast it could go into a pole. It's very easy to do. In software, it doesn't hurt. We take the red car, take the shiny new server, and we hit the gas all the way. How do we do that? We hit it with a load generator. Let's see how fast this thing can go. And when you do that, when you saturate a system for fun, you will get hitting the pole. You will get bad behavior by definition. If you don't get bad behavior, you haven't saturated it enough. Now, it's useful to figure out how fast it can go while it hits that. It's a good experiment to do once. But as I like to say in software, try not to run red cars into poles more than once a day. It's an okay validity check, but the purpose of the experiment is to figure out how fast not to go. Not to figure out what latency behaves like when you go that fast. It'll behave badly. You don't need to spend a lot of time thinking about it. You certainly don't need to spend the next 3 weeks of your time trying to improve how it behaves when you hit a pole. That would be the same as driving this car into that pole, then getting out of the car and say, well, that wasn't good. Maybe I can make the bumper have a different shape next time I hit the pole. Let's work on that problem. Then you repeat the test many, many times. That's what I see a lot of people do when they do load testing. They run the thing into the pole and say, that's not good, maybe I can make it better. Let's run it into the pole again. The actual thing you're supposed to do here is figure out how fast you can drive the car without hitting a pole. It is important to figure out what happens when you do hit the pole to know not to go that fast, but then find other speeds that this doesn't happen at. Now, once you've established that, you can spend your time on improving that. Improving that means, can I go faster without hitting the pole? Maybe I can improve the car. Maybe I can give it better tires. Maybe if the driver wasn't drunk, this wouldn't happen. These are all kinds of things you could do to improve this avoiding pole behavior. So this is not the sustainable throughput. This is not where you want to spend most of your time testing. The reason I'm highlighting this strongly is this is where I see most people spend most of their time testing. It's a waste of your time. Don't do a lot of it. Remember, I'm not saying don't ever do it, just this is not the main data point. What I do recommend you do is do a lot of tests at different levels, at different speeds, at different throughputs, and compare how the behavior looks for each. This is an example of how you can look at 6 different tests and compare them. Each one of them is a different scenario of some sort. Or maybe they're the same scenario repeated, I don't know. You could have improved the code, you could have changed the load, you could have gotten a bigger system, whatever it is you did there. And some of these fail and some of these pass. Now we could start playing with, hey, what's going on here? What can I do to make it better? Can I improve or carry more load and still be in that category? That's the way to play that's where you should spend most of your time. Now, one additional recommendation when you look at this is, you see there are clearly 3 failing and 3 passings in this group, right? Now, if we need to be able to do that blue thing over there, that blue line, and that scenario, we're trying to make it pass, we could go work on the code and find some places, figure out why it's that bad at those paces, maybe tune the system in different ways to get the percentiles to where we want them to be. We can do that. But before you do that, I highly suggest you do one thing, which is to go back to the requirements and say, is that really what we need? Because those requirements are often made up. And you might find that if you went to the guy and said, hey, I'm failing your 80 millisecond worst case thing, can we just change that to 100 and go home? You'd be surprised at how often people say, fine. 80 was an estimate. You don't need to spend the next 6 months of your life making it better, right? So look at requirements as something that's somewhat fungible as well. So you can move them, or you shouldn't move them, but you can ask for permission to move them from whoever set them. Now I'm going to do a little bit of product bragging, so warning here. This is how we use this methodology to show that our product is better than a regular JVM at doing something, right? Remember, I told you that I got into this subject because I need to show off. We actually need to show off to sell our product. So how do we do that? And keep in mind that we use this to show off, and so what we do better, you could do this for you making the code better or you tuning something to make it better, whatever it is. What we're looking at here is a message delivery system. Its job is to deliver a certain rate of incoming message to a number of endpoints. Think of delivering telemetry for games or market data to desktops, right? So thousands and thousands of endpoints to get a stream of data coming in. The metric here is how many endpoints for that for a constant message rate. Now, we're comparing 8 different scenarios. 4 of these are hotspot, 4 of these are Zing. You can see the hotspot result for 15,000 endpoints. Now, to be very clear, hotspot was able to carry 15,000 endpoints on this system. Every message got to its destination, right? This many widgets per second did move through the system. It has the capacity to carry that if you don't care about response times. But if you do have a set of requirements, it's failing them badly in this case, right? These are the requirements, that red line. Now, what can we do? We can lower the load, see if it gets better. So lower load at 10K, it is better, but still failing. Another lower load at 5K, it's much better, but still failing. When you do show requirements, remember that requirements are pass-fail binary answers. You don't say, hey, I met 97% of the requirements, let's ship, right? You're supposed to meet requirements. So here we had to drop the endpoint count all the way to 1,000 to pass. That's a 15-to-1 ratio between the peak demonstrable widgets per second through the system, if you don't care about response time and SLAs, to what you would actually be willing to run the system at if you cared, so the phone doesn't ring off the hook with complaints. 15-to-1, right? Now, at the bottom here, we have Zing doing the exact same test on exactly the same software and system, and there's a 1K, 5K, 10K, and 15K. They're actually so close together that you can't tell them apart, but there are 4 lines there. And this is not really a surprise. Those bumps came from GC pauses. It's a Java-based system. We took away the GC pauses, therefore it got much better. And this is showing that Zing can also carry 15K, just the number that hotspot carries through, but with an SLA. Now, I can't say that Zing made the system's throughput higher. System can handle 15K either way. I can say that it can carry 15 times the throughput within requirements as hotspot does. So as far as how many systems you need to carry this within your SLA, that's 15 times better. That's a pretty extreme case. I usually don't try and set expectations that high. Most people are happy with 2 or 3 times better. Or some people don't even look at throughput, they just want the SLAs to be better. But this is a good example of how to compare. We end up showing this to a CFO or a CO and they understand, right? So it's also a way of saying, look at what I did on the weekend, I want my bonus, right? It's a way to brag. Okay. So I'm gonna switch into the scary subject of coordinated omission now. So before we do that, I want to make sure we clear any questions that might have come up so far. Questions? I'm wondering, should we do a little break in the middle of a 3-hour session? Because we're 90 minutes in. Okay, I think we should do that. It's just 3 hours straight of listening to me talk might be a little bit of a problem. So let's break for 5 minutes. Okay, so be back here in 5 minutes, okay? Or just walk around and don't go anywhere, but stretch out. Thanks.
I will give you.
We're
Yes,
here.
yes, because of yes.
So maybe that's why. Maybe we just don't have
I
it.
will give you. Just give me 5 minutes at the time of the break. I will find the one of the DevOps sponsor. I have it. I get it and.
Thank you.
So first do this, then see what happens. Yeah, it's a good start. A lot of it is you know, I think they didn't mention power management. I didn't put it on the list. Yeah, I kind of assumed it. So, you know, when you run Zing, so you know, the reason I don't mention power management is Zing will refuse to run if you don't clear the site. So class me up. Yeah, the icons, they're overrides, and we have had to override them after. Yeah, those are, well, but the idle driver, setting the idle driver to 0, and then we have, you know, all the processors, like all the questions actually have buzz processor, where under 60 levels, and it turns out that, for whatever reason, run with that load too long, something happens. But when you just keep setting it back, actually, we don't know who's setting it back, so we're just fighting it. If it was supposed to stay, or the processor. Well, the kernel setting to the processor. Because you get good time, the override. I don't know what it is.
Bah en fait,
Amélie, on ne consulte pas, c'est du
Hi Gil, I'm Bryce. We just discussed by email. I will give you the speaker, the sponsor.
Yes. So let's see that. I'm not sure yet if I'm actually gonna use it, but it's good to have it in there.
Yeah. So are you connected on the sponsor? Oh yeah, perfect. So Wednesday is SPO. Oh yeah, and the space, the Wi-Fi is not great. You can enter whatever, just whatever. And well, maybe. Okay, you have to accept, and now the MAC address is registered on their side.
Okay, tomorrow. I don't think I won't need it for the top.
Well, just anyway, you can ask.
Okay. So let's.
S'il vous plaît, messieurs.
Okay. Let's everybody get back. We'll continue. Okay. So let's quickly recap what we covered so far. I talked about philosophy and motivation, why we even measure this, that it's important to think about the measurements themselves. It's important to have requirements and to look at your behavior against those requirements. I showed you what happens when people only state a few points of requirements and forget to state worst cases or higher end spectrum things. And I also told you that if you show your CO that they'll change what the requirements are. And we looked at least I tried to tear down some of the notions of thinking of outliers as things to throw away, thinking of average and standard deviation as meaningful numbers. Neither one of those usually have any, they don't give you any kind of intuition for the actual behavior of response time. Medians, by the way, those are valid numbers. There are real numbers that happen at the median. Half of them are below that. That's a valid thing, but average is just a random number. It really is just a random number. It could happen anywhere in that range. And then we looked at, some intuition about how we think or plot response time compared to load, and what modes look like, and a little on how to test, how not to test, and some examples of actually how to test and compare things. Now, all this stuff assumes that if you measure response time, the measurements that you have actually show numbers that really happened or are representative of stuff. If you show your 99 percentile, your 99.9 percentile, that was the 99.9 percentile of what really happened. And unfortunately, there's a problem with that. The bad news is that most of our measurement systems have a common conspiracy going on that is changing all of your numbers and making all those not true. And I noticed this first a couple years ago, and I thought it was localized. I thought it was a problem in one system or in a few systems or in one measurement technique. And then I saw that pretty much everywhere I look, this problem happens again and again and again. It repeats itself. So I right now basically assume it's there unless I show that it isn't. It is that strong. I call it an accidental conspiracy because none of us meant to do this. The people who write the code to do this don't do it because they mean to mislead. They actually want good numbers, but the math works out wrong. So I'll go through what this thing is, coordinated omission, what makes it happen with some examples, and then how bad it can get, and we'll talk about it some more. So when I say coordinated omission, it's pretty simple. The word coordinated and word omission are common sense. Omission is dropping, it's throwing away some things. So I have a lot of data points. I got rid of some of them. And omission on itself, on its own, is not wrong. If you want to establish percentiles, you can establish them by omitting some. It's okay to sample. The only number that it's not okay to sample on is the max or the min, because you probably want to cover those. But pretty much every other stat you want to look at, it's okay to sample as long as you have enough data points. If you had 1 billion data points and only kept 1 million, I can still establish a good number of nines from that, and I'm probably okay. As long as the things I threw away were not coordinated with the behavior of the system. So as long as my omission is valid, uncoordinated, random or semi-random, I'm okay. The problem is if I throw away data in a coordinated fashion, if I only throw away certain types of data, only the blue data, then ask what the color is, I'll get a skewed result. Right? So how does this happen, or what are the common cases? There are many things that will make coordinated omission happen. These are the common examples I run into. The first one is load generation, load testing, the thing we do in the lab to figure out how many things per second something can handle and what the latency behaves like when we handle that many. Now, load testing is done in many different ways, but most commonly you get somebody else's load tester. You get an open source one, or you buy one, you use a tool somebody else built, and you use it to beat up your system at a certain rate. And there are many types of these, but most of them tend to have some scenario being played. So a client will issue a request or a message, will observe the response, and then do something else according to plan. Now, you could have testers that do this on many clients at the same time, but for an individual client, there's a serial operation being done. Request, get the response, then send the next request where we're supposed to. Suppose I'm supposed to do 10 requests per second in this client. I send the request, I get the response. Now I wait until 100 milliseconds have passed from my original time of sending the request, and I'll send another one. That's commonly how it'll happen. And a lot of times this serial behavior is necessary because of application logic. First log in, then do whatever I do when I log in. First ask for the web page, then find the link to the image I need to display. They're dependent on each other. I can't just run them in parallel. So the clients are often forced to do the operation one by one because that's what the application logic really requires. So we take all this stuff, and the clients send a request, take a response, record the response time or latency in a bucket, and later we're going to do analysis. Right? We'll look at the spectrums, we'll do percentiles, we'll plot them or do whatever we want. What could go wrong? Right? Well, this methodology works correctly only if every single request you send had the response come back before you were supposed to send the next request. When you test a load, when you ask a load generator to test a load, you gave it a plan. You tell it to run at this speed. It's supposed to run at that speed, which means there's a time that it's supposed to send requests on. As long as it sent all the requests on the times they were supposed to be sent, everything is good. But if you have a response that takes a long time, and because it took a long time, the next request that was supposed to be sent wasn't sent on time, you just coordinated with the system and backed off and didn't send the load when it was actually misbehaving. And then you later measured the thing you were supposed to measure now at a better time to measure. That coordination will skew the results. You've avoided measuring things when it was bad, and instead, often you measure things when they are good. And that coordination can skew results dramatically. So this is load generation. In a load generator, this often happens. The other common example is not load generation, but monitoring. When you measure the speed of your execution in your code, in order to report statistics to a monitoring system or just do whatever it is you need to do with them, you often do something like this. Take time before, do the operation, take time after. The delta between those two times is how long it took to do the operation. Let's record them in a statistics bucket, and later we'll analyze the bucket. Okay? There isn't really much else you can do. I don't know how to measure the length of an operation other than that. But the problem here is that these results could be highly skewed in one of two common ways. The first one is, imagine that the system stalled in the middle of that operation. That one operation took a really, really long time. Now, I will have one result that has a really, really large number in it. But I might have 1,000 things waiting to get into this code, and my stats aren't showing that they're waiting, and that I'm keeping them from getting in there. So I'll have the stat of how long that took, but I won't have the stat that's relevant to anybody actually executing it. Worse yet, that's the first case. I have one bad result in just avoiding a lot of other bad results, omitting them. But worse yet, if I measure this in more than one place in the system or in only part of the system, I might miss the stall altogether. So for example, this piece of code comes from a version of Cassandra. And this is how Cassandra measures the read latency that shows up on Cassandra consoles. This is where the 99th percentile latency that Cassandra reports comes from. Okay? Cassandra is often used not as a read mostly database, but often is a write mostly database. It depends on the use, right? It's actually really good at doing that. So sometimes you'll have 5% reads, 95% writes. That means the likelihood of a stall happening in the write rather than the read is very high. I might actually have a stall that is simply not measured here. It's outside of this code. And when that happens, I wouldn't even have that one data point that shows that something was wrong to suspect it. Now, all the examples I give so far are examples of omitting results in a way that coordinates with bad behavior, of omitting bad results, not just results. And usually when you talk about this, people kind of say, I understand, I mean, this will happen, it'll skew a little bit, it's going to be noisy, but it's rare, it'll only happen on outliers, right? How bad can this get? So let's look at how bad this can get. I'm going to run through a hypothetical scenario. This is a system that we define to behave in a certain way rather than build to behave, and let's describe it. This system is going to be run with one client thread. If you want to think of something with 1,000 client threads, just multiply this by 1,000. But one client thread, and its request, it's going to answer exactly 100 things a second, or it's going to be asked 100 things a second. It will behave perfectly. Every request will come back in exactly 1 millisecond. That's how this system would behave. Now, we will take this perfect system, let it run that way for 100 seconds, and then stop it for 100 seconds. Completely stall the system. Hit Control-Z on the keyboard, wait 100 seconds, come back. And then we'll repeat this. So every 200 seconds, you have 100 good seconds and 100 bad seconds. Now, what can we say about the behavior of the system? If we wanted to summarize the many, many results we'll measure, how would we summarize them? Let's do a little bit of math. And there are no tricks here. On the left, we know the average will be 1 millisecond. That's all it does. On the right, in this stalled 100 seconds, the average will be 50 seconds. Why 50? Because I'm stopped for 100 seconds, and depending on where I come in to measure, it'll be some number between 0 and 100. On the average, it'll be 50 if I do this many times, right? The overall average over 200 seconds is the average of the two 100-second segments. If I come in randomly within this 200 seconds without asking, are you ready? Then I'll, on the average, take 25 seconds to answer a question. We could also look at percentiles and make very simple, clear statements. The 50th percentile of this system is very good. The good half is very good. But then things go really bad. The 99.99 percentile of this system is very close to 100 seconds. These are all intuitive, honest ways to describe a system if this is how it behaved. Okay? Again, I'm not trying to trick you here. These are simple. This is the math behind it. If you reported, if this happened and you told somebody this happened, you would be honestly describing the system. Let's go measure this system with a load balancer or with a encode time delta and see what we would get. So what would happen? On the left, we will get 10,000 results that each have 1 millisecond. On the right, the system stalled. So we will get one result that shows 100 seconds. And we're not doing anything else. After 100 seconds, we'll do the next things. That's all the data we have. That's what's in our statistics bucket. Let's do the math on this. The average of that is 10.9 milliseconds. It's a little lower than 25 seconds. More importantly, the percentiles are really, really good. I mean, this system has got a really good 4 nines. The 99.99 percentile is still 1 millisecond on this system. Now, this is clearly a lie, but that's what your measurement systems will tell you if you measure with the common techniques that have coordinate omission. So what happened here? Why is this so wrong? Well, the answer is pretty simple. If we measure 10,000 things in 100 seconds, we're supposed to measure 10,000 things in any 100 seconds, not just when it's convenient. And had we measured 10,000 things during the stall, we would have gotten all these numbers on that line, and the numbers would have come out right. And we would have had an honest description of the system. When you report percentiles to somebody, this is what they assume that you are talking about. They're not the percentiles of the good stuff that are good. It's the percentile of this stuff. Which basically means if I come in randomly, or in the future, what is the chance of me seeing the result X? That's what percentiles mean to people. So when you report percentiles that don't mean this, you're lying. Flat out lying. Not, just saying something true that is meaning something else, right? Now, what happened here? Coordinate omission is basically the erasure of bad results. Selective erasure of bad results. And it happens naturally in most load balancers and in most monitoring systems. Which means the stats that you're looking at are highly optimistic. They're not the percentiles of what happened, they're percentiles of the good stuff that happened. And that's very unfortunate. So that's basically what we're looking at, a skewing of results as a result of that. Now at this point, you might say, okay, that's scary. The numbers aren't right. But I often deal with people saying, you know what, okay, the monitoring is screwed up, the load generation is screwed up, the capacity planners have a problem. But at least me, I'm a developer, I can at least tell if things are getting better or worse. I can look at the numbers for trends, not believing what they actually mean, but better is better and worse is worse. So let me just debunk that myth for you, because we actually spent a few months chasing our tails because of that myth, and that's almost what started me with these slides. Let's take this system and improve it dramatically. Rather than stall for 100 seconds, we will answer every question during that 100 seconds, but unfortunately it's going to be a little slower. Instead of 1 milliseconds, it'll take 5 milliseconds. But every single question will get answered during that time, at that throughput. Okay? Now, we improved the system, right? We made it better. It's unquestionably better. So let's measure and see what our load generator would tell us about that engineering effort we just did. We would get 10,000 results at 1 millisecond and then 10,000 results at 5 milliseconds, right? If we do the math on that, it'll show that the 4 nines moved from 1 millisecond to 5 milliseconds. So improving the system made it 5 times worse. So I must have done something wrong. This is bad engineering. Let's throw it away and go back to the other system because it's better. Right? That is what actually happens when people apply these tests. You go and you do an experiment. You ask yourself, did this really improve the system? And the measurement system says, no, it's not improving it. It's actually making it worse. Where clearly it is making it better. So the fact that the results are skewed and bad results are thrown away actually reverses the direction of better and worse in many cases. The best way to look good is to put a big stall on the bad results. If you have a period of bad things, it's better to do nothing. Because then all the load measurement systems will say you're perfect. In fact, if you manage to do nothing outside of the measurement window, you're really perfect. That's for monitoring systems, right? So this happens. Now, you can also go from there and look at the next step of what happens, which is what I call cheating twice. So cheating twice is what happens when load generators try and say, oh wait, I missed some requests, let's catch up. This is what a constant throughput load generator will typically do. So you're supposed to send 100 things a second, but we didn't send things for 100 seconds, so we're 10,000 requests behind. So when we wake up from the 10,000 requests, from the 100-second stall, we say, oops, I need to send 10,000 requests here, or 9,999. So we'll send them and we'll measure them. But now the system is good. So not only did we throw away almost 10,000 bad results, we introduced 10,000 fake good results, skewing the results twice in the wrong direction. Unfortunately, this is what happens. So it is happening to you, most likely. How many of you use JMeter? Oh shit. Okay. Here's how JMeter reports on the scenario I just showed you. That top chart is what JMeter would report if you test that simple control Z test. You can go home, repeat it on your own test and see. The bottom chart is what JMeter should report. It's actually that's from a corrected JMeter log. We took a JMeter log, corrected it to have the right results that are missing, and do that. And by the way, in JMeter, it's very, very easy to see this, because if you look at the JMeter output, you look at the log, there's a gap in the log. Every time you pause, the timestamps have this nothing happened, and then they keep going. That's the, somebody went and erased your data. It's not intentional, but it's not there. And correcting is simply, let's reintroduce the linear missing results. That's what that correction was. And you know exactly what to reintroduce because you see what the rate was supposed to be. You see how big the stall is. You know how many missing results there are. You know how big each one of them would have been. So it's easy to correct. It's just, manual. So JMeter, Grinder, and pretty much most commercial load balancers do this. Bad news. Now, not just load generators, benchmarks. This is YCSB. YCSB is a benchmark used to measure the capacity and the behavior of key value stores. How many of you use a key value store for something? Okay. So how do you know if you have a big enough set of servers to serve your load? It's a benchmark like this or something like it. Somebody's banging on them saying, okay, how many am I doing and how is it responding? How many of you use YCSB for that purpose? Okay, good for you. By the way, this is academic benchmarking of key value stores usually uses this. So there's several academic papers where all the results and all the plots are based on this tool, which tells you what they're worth. Now let me show you the actual behavior that's easy to deduce just from some summary. And this is an example of sanity checking with very little data. This is a test that we happen to know is a single-threaded, single-client test. That's how the test was done. That's a typical way to run YCSB, a typical way. It took this long. Now, during this test, we had one result that we know was really, really big, 26 seconds. Not a big surprise. This is Cassandra with a 20 gigabyte heap. Sometimes this happens, right? Not an accident. So we know that in a single client test, there was a result that took 26 seconds, which means we know that there were 26 seconds when nothing was measured. Okay? And since the result took 26 seconds, the system was probably stalled during that time. We know it was because we saw the GC logs, but that's a good hint right there. Because that number is so big, it's more than 1% of the run, we could do math about the 99th percentile here. We can subtract 1% from 1.29%, and the remainder is the best possible 99th percentile you will have. So we were stalled for 1.29%. We can forgive 1% of that within the 99, but we can't forgive the rest. 0.29%, the remainder is 5.9 seconds. The best possible 99th percentile in this run was 5.9 seconds. That's 1,000 times what the benchmark is reporting the 99th percentile to be under load for this key value store. If you were capacity planning based on this, thinking that you'll get that 99th percentile with this system under this load, you're 1,000 times off in what that will behave like. Bad news. Okay. Remember, this is a sanity checking exercise rather than the 1000x off. Here's some results from an actual system. This is a payment settlement system. And it's an online payment system, and it's supposed to, the SLA was for the 99.9 percentile to be better than 1 second. Over here you can see that it was. That's what the data in the lab and the monitoring was showing, that it is better. But when we corrected it, you see that it was 7 times worse exactly at the requirement point, which was also the difference between pass and fail. The issue here was all the data was saying, hey, this is good, but production was failing SLAs from the outside, right? Now, this is the first chart where I'm showing you coordinated omission visually on a percentile chart. It's very easy to see. See that vertical rise? That's a telltale sign of coordinated omission. Anytime you see a vertical jump in a percentile chart, suspect coordinated omission. There are some other things that look like that, but they're very rare to see in the wild. Here's another example. This is from a Wall Street trading application. Pretty impressive application. It's equities system. It's doing on the order of 100,000 things a second at market rates. Common operation in and out of the system in 9 microseconds. Pretty cool. In Java. So if people tell you Java can't be fast, it can be fast. But unfortunately, it has outliers every once in a while. And you can see how big those are. The problem we were actually facing here was not whether or not there are outliers and where to fix it. You remember, we go in and we eliminate pauses, which these are, and we got rid of them. The problem we had was explaining to the purchasing people why you need to buy a system to improve your 8 nines. Look at how far to the right this is. I don't even have 9s on this. This is the 6 nines over here. So the big problem, the thing we with Zing were improving, was extremely rare. Why do you want to spend money on this, right? Well, we know it's not really that rare. We know there's a measurement problem here. So I actually flew to New York and sat down for a whole day with the people to work on this code, because you actually couldn't make this happen in the lab. You had to be siphoning data from the real market in real time to get these behaviors. Like in the lab, you couldn't reproduce them. Which is, by the way, another interesting thing that I run into. Very commonly, your production behavior is not reproducible in the lab from a latency behavior point of view. And people spend months trying to recreate reality in the lab unsuccessfully. As hard as it is to stomach, often the only way to really study things is to take a real production feed. Hopefully a feed that doesn't involve actually changing production, but just listening to it, which we did here. But sometimes you actually have to run in production to measure. The lab is often really hard to measure reality. This is a good example where these stalls just weren't happening in the lab, but they were happening constantly in production. You can spend a lot of time trying to recreate reality, or you could just use reality instead. Anyway, that's the uncorrected data. And this is a classic in-system measurement. Take the timestamp as the packet arrives, take the timestamp when you send the packet out, do the delta, see the difference. That's how the code was measuring where the data comes from. So we went and we recreated this data using, I'll show you the HDR histogram tool in a minute that I use for that. And then we corrected for it. So every time we had a stall, we filled in the blanks. And this is what the corrected data is. That's a big shift to the left. And by the way, this correction is a conservative correction. Only 1/3 of stalls is actually corrected in this set. How do I know that? We had the GC log for the system, and we saw that there were 2/3 of the GC logs logged by the collector did not show up as a stall in the measurements. So the measurement system didn't correct them. But 1/3 did, and that's what the correction is for. Now, the reason I cared is Zing was doing this. Corrected and uncorrected are pretty close there. That's what the other JVM was doing on the same system. And this is a 2500x difference in the notion of how often what we do makes a difference. From the 8 nines down to the 5.5 nines, or Since this system's doing 100,000 second, it's from the 8 nines to this affects every second of operation during the day on average, which is a big deal. So this happens a lot. Again, how many of you follow Kelly Summers on Twitter? You know who she is? Okay, several. Those who don't, you should. She does a lot of interesting stuff in experiments in the wild and makes mistakes or does brilliant things or everything and just honestly talks about it. Anyway, this is her posting a comparison of a before-after with coordinate omission on a test that she's been doing. The blue line is the way measurements were done before. The red line is the reality of what was happening, non-coordinate omission, with a little bit of a difference across the spectrum. This is a nice comment about the blue pill and the red pill. You know, once you see that red line, once I tell you about coordinate omission, I can't take it back, right? And then, the natural reaction is, realizing that all that data you have needs to be thrown away because it's wrong. And you need to remeasure everything right. So, I go around converting one person at a time. Here I get to convert maybe a couple hundred people or 100 and some people. We'll see how many of you actually believe me at the end. Anyway, when we look at this, I'm going to summarize to this point. The very first thing to realize is that anytime you do a test with something that measures data, verify the test system before you spend any time believing the data. I had a physics professor in my freshman year in engineering who taught me a really hard lesson in a really hard way. He was great at doing this to freshmen. This was a physics lab. And basically he set up all the lab experiments for everybody, and you had a 2-week project where you measured a lot of things. You issued a lab report. You learned how to do that. And everybody failed. And the reason everybody failed is that before the 2-week experiment, he went and messed with everybody's instruments and made them all give him wrong results. But make them give him wrong results in a way that within the same test bench seemed to make sense. They were not just wrong and inconsistent, they were consistently wrong. And then you spent 2 weeks of your time and you issued a report and all the data was wrong and he knew it. So unless you came in with, I had to recalibrate my tools and then this happened, he would fail you. Test your tools, calibrate them. Don't use any numbers that come out of a non-calibrated system because you're wasting weeks of your time and you should fail. Specifically, if JMeter will lie to you on a test that you know the answer to, why would you believe anything else it says about latency? Why would you put your job on the line for that, or your weekend on the line for that? And I'm not saying JMeter is a bad tool. It's a great tool for stressing a system. It's a really good way to run scenarios against the system. It will make the scenarios happen. Just don't look at the latency output from it and believe it means anything. That's not what the tool is good for. Unfortunately, it claims to report them. So test the test system with understood, well-known behaviors to verify that for something you know the output needs to be a certain way, that's what you actually get back out. It's Physics 101. And then don't waste any time trying to analyze the bogus results that come out before you did this. And I am telling you, if you go back to your current results, you're probably going to find a lot of results that come from tools that fail basic calibration, which means you are looking at junk and you are wasting your time. Now, we talked about standard deviation. Don't ever derive anything from it. I highly recommend that you stop reporting it or putting it next to latency numbers. It distracts people. It makes them think that the latency number has some behavior that's normal next to it. Otherwise, why would you have put the standard deviation there? Always measure the max time. The max time is the one measurement that's usually hard to hide from. Yeah, you can omit it when you monitor, but in the load balancer and the load generator, it's really hard to avoid seeing the maximum time. And it's your number one sanity checker. I showed you an example of how to take just the max time and say, if this max time exists, these other percentiles couldn't be right. So you can sanity check with it, and then measure percentiles. Measure lots and lots and lots of percentiles, as many as you can. So that's a little bit of summary of what we saw so far and of what to deal with in coordinate intermission. I think we're going to have time, and I'll show you an example of correcting coordinate intermission in an actual load generator. Assuming the fonts are going to be well enough here to see stuff on the screen. But the first tool I'm going to look at is HDR histogram. So I told you to measure a lot of percentiles. How? One of the unfortunate things that I see is that lots of times people will collect a lot of data. Now, if you can keep all the data, you're good. If you can log every single result and never throw the log away, that's good. But if you're actually doing thousands of operations per second, often the act of logging will ruin your system. That alone might create problems. So if all you want is to know the behavior of latency, people often summarize that behavior in some way. For example, they might do the stats every second, or every 5 seconds, or every 10 seconds, send them to some server, or put them on a log file, and that's it. And when we look at those stats are usually for that period of time. If I'm doing 1,000 things a second, and I'm reporting every second, I can't know what the 5 nines are, right? Because I only have 1,000 things in each second. And I can't take the stats from this second and that second and that second and take the percentiles from them and derive something else about them. If I just report, say, min, max, some percentiles and the average, there's nothing I could do that will tell me what the higher level of nines are across minutes or hours. Unless I keep all the data or use something like this. So HDR histogram was actually built so that you could get this kind of fidelity, this kind of resolution on percentile reporting, so you could start looking at shapes of percentages rather than 3 numbers summarized with low nines. I do believe, by the way, that the reason most people don't look at the high nines is not that they don't care, it's that it's hard to measure them. So this is a tool that makes it easy to measure. Now, to be able to look at this kind of chart, you need both a good dynamic range and good resolution at the same time. What do I mean by that? Dynamic range is the vertical axis. If I'm building something to measure latency and I don't know what you're going to do with it, I don't know what the range of latencies will be. And I also showed you that 1000x range is very common. And the tool may be used across 6 or 10 orders of magnitude of possible latencies, right? Within a data set, you may have 3 or 4 orders of magnitude, but you may be measuring microseconds or milliseconds or minutes, I don't know, right? So I need a good dynamic range. I also need a good resolution, because if I, say, quantize this to binary buckets, then the top right quarter of this chart would be one big pixel. And I wouldn't be able to see the shape in there. So dynamic range is, how much to cover. The resolution is the kind of the level I can distinct within a level in there. HDR histogram basically lets you do both. It's a high dynamic range histogram. You can configure the dynamic range and the precision within it. For example, you could say I want to cover microsecond to 1 hour, and I need 3 decimal points or 2 decimal points of resolution within that. You can configure it to do that. Now within this, it has built-in optional compensation for coordinate intermission. So if you know not just what the latency you saw was, but what the sample rate was supposed to be, you can tell it, hey, here's this latency it was supposed to be with this sample rate, and it'll fill in the blanks for you. You don't have to use this, but it's useful for when you actually have a test system with a known interval. It's really fast. By fast, I mean this laptop can record 200 million results a second into an HDR histogram in a single thread. That's faster than I can measure time on this laptop. So if you can afford to measure time, you can afford to store that time in an HDR histogram. The data structure is fixed size, zero allocation, and fixed time. So it's fast, and it's not going to keep growing on you. You can record 1 trillion operations into one HDR histogram. It's not growing or shrinking or doing anything like that. And it's very, very open source. The best open source. It's public domain. And for people who for some reason have a problem with public domain, it's also dual license under BSD. But it's public domain. Go do whatever you want with it. Just don't blame me. Okay? Now, I created a Java version of HDR histogram, and people have been using it in Java, but also porting it. So there are now C#, C, Go, Erlang, and I think there's a Python port being worked on, or I've actually seen a prototype of a Python port. I'm waiting for somebody to do a JavaScript port. I don't want to do it myself. Any volunteers? Okay. It would actually be very useful if we had one. It's just a pain. So there are now multiple implementations of the same data structure. It's basically a data structure with an API and in the same behavior. And one of the good or useful things of that being true across multiple languages environment is there's a logging structure to HDR histogram, a logging format, where you can take an interval histogram and log it in a compressed form. And all the libraries support the same compressed form, so I can log in C and display in Java or analyze in Java, for example. The compressed form is very, very compact. So an entire histogram, for example, a 2 decimal point histogram from a microsecond to an hour, which I regularly use, will compress down to a couple hundred bytes, which if you do one, say, every 5 seconds, represents low tens of bytes per second of data to capture a full fidelity, lossless histogram of what happened. Now, the really good quality of it is because these histograms are covering counts at levels, they're in the domain where percentile analysis is valid across time. If I have a histogram for every 5 seconds, I can reconstruct correctly with no loss the histogram for the last hour. I could go back in time and say, yesterday between 8 and 8:05 a.m. something strange happened. What was the distribution of latency during that time? Without knowing ahead of time, that's what I'm going to look at. So you can add up histograms and get a histogram for a larger data set, either larger time, or for example, if you have 15 servers and they're each logging, you can get the histogram across all 15 just by adding them up. And then you could do percentiles on that. So you can get your percentile for the hour, even though you're only reporting every 5 seconds, because you haven't lost the data that would then make percentile math wrong. This makes it very useful for production logging, and it's used by several tools. J-Hiccup is one of them, and I'll talk about J-Hiccup in a second. There are other people who have been using it for monitoring tools, and Aaron and a few others are using it. I've started seeing people use this format of chart in presentations, so I take snapshot whenever I can. If you see a chart like this, I'd be happy to know about it. This chart is actually an Excel sheet that's up on GitHub. And what we're really plotting there is the summary of a histogram data in a format that CEOs can read. Okay? If you think about that, this is actually a logarithmic chart, right? But if you said 1, 10, 100, 1,000, most lay people won't be able to follow what this is. So percentiles make it easy to understand what it means. What we're actually plotting is this function. The x-axis here is the log of 1 over 1 minus percentile. It's not the actual percentile, right? But that makes it readable on a chart. Now, because you need to do this math, the output of HDR histogram, there's a common output format for a summary histogram, actually gives you columns that pre-compute the axes. This is the value level, which you would need anyway. Here's the percentile level, and you can see this is kind of a sort of a cut the distance to in half all the time, kind of report by 10% up to 50, then by 5% up to 75, then by 2.5%. Keep cutting the resolution on percentiles until you run out of data. So that's what this is. That's the actual percentile. But for plotting, this is 1 over 1 minus percentile, so you can plug it into Excel or GNU plot or whatever it is you do without having to do the math yourself. So the output format is convenient for that. All this is up on GitHub if you go to hdrhistogram.org. Here's what the front page for that looks like, and there's now a convenient online plotting tool where if you just press that button, you'll get to this page, and that page has a, point to my files thing. This is pure JavaScript. It's not uploading anywhere. This is your browser using your files and plotting them, and you'll get the plot of your data. And all of those variants of HDR histogram will output the format that this reads. So whatever language you're running in, you can actually take the output and get these nice plots for your data. And you can do all kinds of nice things with those plots, like compare them and see good versus bad or correct versus incorrect. One of the things I like to do with that is try to look at the shape and try and guess what the system behaviors are that cause that shape. So remember when I showed you this, where that bad news is this is not a normal distribution? Well, that's not just bad news.
Good news, everyone!
Yeah, there we go. This is my one audio recording thing. Yeah. The good news is that there's information in your data. You have 1 million data points, and no, it's not just 2 numbers that characterize them. And because it's more than just those 2 numbers, that means the shape has information you can try to learn from. So let's try and learn from it, and let's try and show some of the common shapes, or the non-common ones. So what would constant latency look like? Well, that's an easy one. This is what constant latency would look like on a percentile chart. Pretty easy to understand. You will never see this. But if it happened, it'll look sort of like that, right? What will Gaussian latency distribution look like? This is Gaussian. This is a 10K level plus a Gaussian noise with a 5K standard deviation. Okay, so both above and below. That's why it goes below 10 and above. As you can see, it keeps growing and growing and growing, because remember, this is a log chart. These are less and less likely by orders of magnitude. Again, you will never see that. Okay, but this is what they would look like if they happen. What does random look like? Often people think random and Gaussian are similar things. Well, they're very, very different here. That's what a random distribution of noise on top of a 10K is. So this is 10K plus 5K random, not Gaussian. Now let's think about that to explain intuitively why they're so different. In the Gaussian case, the farther you go, the larger the contribution. It'll keep growing forever. If I go to 100 nines, it'll be really big. In random, I said this is a random number between 0 and 5K. It'll never be bigger than 5K. In fact, by the 90th percentile, I've covered 90% of the distance to 15K. So I only have this much left. That's why it's asymptotic to a straight line, right? So random and Gaussian, 2 very, very different things. What does stalling look like? This is what stalling looks like. You saw several of these multi-hump things and stalls here. If you stop a system, and then you actually sample during the stop, not stop and don't measure, but stall and then measure at the same rate as you measured without the stall, that's the distribution you would see. That scenario here is, it's a 10K fixed plus a 50K, is that 50K? Yeah, plus a 50K stall. The likelihood of the stall is there, and the measurement interval is 100 of whatever that unit was. Okay? The measurement interval is important because that's the drawdown rate there. By the way, all these scenarios are created by something I call histogram generator. It's also on GitHub. There's a link to it at on the slide. This is what queuing looks like. Now, when I first did this, I actually expected queuing to look exactly like stalling. Because if you think about it, stalling means I just stopped, and the first result will take a long time, the last result will take a little time. So it's kind of like that. And queuing is almost exactly the opposite. I get a burst of stuff. The first result comes out quickly, but the last result in the burst will take a long time until I get to it. So it's like that. But distribution-wise, they should be the same, except that if you look at queuing as a probability of seeing a burst, when you stall, nothing happens. When you have bursts, then you could have a burst happen in the middle of working on another burst. So that's why you end up with these multiple humps. The first one is, there was a burst. The second hump happens because a burst happened before we finished processing the first burst. The third hump is the same thing and twice overlap, and so on, right? And yeah, if we kept going with the 9s, it would keep growing. Remember, these are orders of magnitude less in likelihood. And then the last one is a true multimodal data set. So for example, I have an operation that sometimes takes, sometimes takes 70K, sometimes takes 10K. It doesn't do anything else. And the likelihood of the 70K is 1 in 100. That's what this would look like. So not only coordinate emission has vertical rises, right? And there's a 180K likelihood there, you can see as well. So these are just, if it behaved like this, this is what it would look like. It's nice hypothetical games. None of these are real data points, right? They're just shapes from a generator. Now, what is this useful for? Well, Kelly posted this when she was playing with coordinate emission comparison. The blue line was what things were showing before. The red line just happened. And she likes to use that word a lot. It's like, what is this? What's causing this? And the nice thing in this, I actually wrote the generator because of this post, not the other way around. So look at this and say, that's strange. What makes a multi-step thing like that happen with some clear regularity? This is not, there's a regular pattern here. What's causing this? So, plotted the different scenarios and then try to pattern match them, right? And from looking at the scenario, saying, what does this look like, and can I explain it with one of those behaviors? So taking a step back here, I actually think there's a common methodology, not just for figuring out where latency comes from, but for figuring out all kinds of mysterious bugs that we use. That in software at least, or in systems, we often apply intuition and go for this mental leap of, that looks interesting, I bet this is what that is. And we're often right. I call this the Monty Python way of figuring things out. How many of you have seen the Monty Python and the Holy Grail? It's a classic movie. Okay. How many have not seen it? Okay, there's a handful. I'll narrate a little bit here. I do recommend you see it. So this is how you use the Monty Python methodology. This is a scene in the movie where a knight is faced with a problem. The crowd wants to burn a witch. They say they found this witch, and see, they put a carrot on her nose to show that she's a witch. And his job is to figure out justly whether or not she's a witch, so whether or not you should burn her, right? So he deduces an experiment to figure this out. And the logic goes like this. What do we do with what do we do with witches? Strike that. They're true. What do we do with witches? We burn them, right? Well, what else burns? Wood burns. So, what else do we burn other than witches? And then, what does wood do? Well, wood floats on water. So, what else floats on water? Right? Now, at each point you come up with questions and potential answers. Sometimes the answers are wrong, like very small rocks. They don't really float. But then you come up with the right answer. A duck floats. Right? Now, since a duck floats, and wood also floats, and we burn wood and we burn witches, if we compared the weight of a duck to the weight of a witch, weigh them against each other, and a witch is lighter than the duck, then she must float, therefore she's a witch and we can burn her. That's actually the logic, and then they have this scene where they actually go and do that. And actually, as they walk away, the witch is lighter than the duck. Now, okay, this is clearly a weird way of doing things empirically, but it's actually very useful. And I know that I do this all the time, and it's very, very effective. How do we do this with latency? Well, does this look like a duck? Or, maybe one of these, and look at that. Oh, look, there's this multi-hump thing that looks a little like the posting. So we found our duck, and, let's go from there. Now, this is not as silly as it sounds. It's very useful, as long as you don't assume that because it looks like that, that's what it is. What we're actually doing is ruling things out. If it doesn't look like that, that's not what it is, right? This is not a duck. This is not a duck. This is not a duck. Now, that looks like a duck. Maybe we should focus and see if we can prove it's a duck. Save us a lot of time, right? So in this set, the only shape I have that looks sort of like the shape that Kelly was posting is this queuing thing. So maybe I could look for a queuing reasoning on what she's doing that would explain it. In that specific case, again, this is theory. We didn't actually prove it. We believe it's because there's a rare likelihood of CPU contention. Rare, but possible. And when there is CPU contention, there's a jump of 10 or 20 milliseconds in the quantum. There's a likelihood of CPU contention will make you wait twice as long in the queue because there's 3 people waiting for the CPU, or 4 or 5. The likelihood of each of those is exponentially lower, but this is a log chart, which shows exponents as fixed distance steps. So, that's the duck methodology for debugging things. Very useful, I think. Okay, so we looked at HDR histogram. We looked at how to measure with it, or I explained that you could go look at the website. There's full Java doc and other docs for it. You can record in it. You can report from it. It's convenient, and what you could do with the output. An example tool, and a useful tool on its own that I use a lot, is J-Hiccup. J-Hiccup actually is a really good example of using HDR histogram. It's all of about 600 lines of code, 300 of which are comments and argument parsing. So there's about 300 lines of actual logic to understand, and that's mostly because HDR histogram does all the work and this is just a wrapper for it. What J-Hiccup does is it lets you plot this kind of chart to see the inconsistencies of execution within a JVM. The J part is Java. This is for Java. So you take and add it to any Java process as an agent, and it'll plot this for your process as it runs, or output what's needed to plot this. And then there's a spreadsheet that does this for you. So what are we seeing here? This is not your latency or your response time. This is the JVM's latency. Meaning, according to this, 1% of the time the JVM was stuck in a 350 millisecond stall. That's pretty bad, but that's what happened in this application. Now, that means that no matter what, your numbers are going to be worse than this. Now, this makes it a very good sanity checking tool, because if your numbers are not worse than this at the 99 or whatever percentile, then either J-Hiccup has a bug or your measurement methodology has a bug. And this has 300 lines of logic in it. It has just fewer room for bugs. So it's a good sanity check tool. It's also a good way of simply establishing the best possible latency behavior you have. If that's how your system stalls behave, that's how long it would take if your logic took nothing every time. It was 0 every time. That's what you would see. So J-Hiccup as a tool is, it captures that stuff. You add it as a Java agent. For demo purposes, there's a convenient attached to a running process script. Although I usually don't like to use that for real measurement, because then you forget to do it again. It's better to actually add it so every time you run it, it'll be there. And all it really does is add one background thread to your process, one Java thread that goes to sleep for a millisecond, and when it wakes up, it says, how long has it been? It was supposed to be runnable a millisecond after the sleep. If it took longer than a millisecond before it ran again, that was a hiccup. That thread experienced a delay. That thread is not special. In fact, it's doing nothing other than this, so it's probably the most deserving of CPU in your system. If it didn't get to run for, say, 50 milliseconds, this JVM probably didn't let anybody run for that 50 milliseconds, or at least that level of effect was affecting other threads, because the thread doing the measurement is not special. That's basically what it does, and it's nice and very open source on GitHub. Now, a lot of people use this now, and one of the common uses, since I added the production logging feature to it about a year ago, is that you could do continuous production logging with it. So it's very lightweight in cost. It generates very compact logs because it's HDR histogram logs. So you can use it to record hiccup behavior in production and later try and use them for triage. It also has a very useful mode that I call the control mode, which basically says when you start it, don't just run a J-Hiccup in my process, but start another idle process that runs right next to me. At the same time, will terminate with me, and run a J-Hiccup there. And that process is doing absolutely nothing other than J-Hiccup. Now that control process basically lets you watch system-level hiccups versus JVM-level hiccups. And this is an example of the triage you can do with this. So suppose there was a problem. Somebody reported a glitch. And you're trying to figure out where or what it comes from. J-Hiccup won't tell you where it comes from, but it could tell you where it's not. So, for example, if I have two logs, the JVM log and the control log, and there was a hiccup, and you look at the logs and you find that at the same time that you had your problem, those two logs show a spike. At that time, there was a spike, and the distribution during that period of time is bad. Then you know that the JVM experienced a spike, but also an idle process doing nothing experienced a spike, which means the entire system saw a delay. So you know you need to look not at your code, and not at the network, and not at the JVM. It's none of their fault. It's the system. Figure out what made the system have this hiccup. Now, maybe it's power management, maybe it's a hypervisor, maybe somebody ran 100 threads at the same time for 50 milliseconds and didn't tell you about it because it's a cron job. One of those. But something happened at the system. Go talk to the people managing the system because the system is noisy. Right? Everything was affected. On the other hand, if you look at the logs and the system, the control log is quiet, but the JVM log is spiky, you know the system doesn't have a problem. You know your code doesn't have a problem. You know the JVM stalled. Go figure out what made that happen. That's where we do most of our business, right? Because most of the time when you look at why the JVM stalled, we know what made the JVM stalled. It's GC, and we take care of that. And then the last one is, well, both of these logs are clean, and you had a spike in your latency. Well, the system was fine, the JVM was fine. Go look at your code, go look at the network, because you don't need to look at those. That gave you a three-way split on where to look. It saved you 2/3 of the work, hopefully. So just that alone is a useful reason to run it in production. It also lets you see and start develop intuition for these shapes for real systems rather than just hypothetical workloads. Here are some examples of using J-Hiccup. The first thing I actually do with it almost always is verify that the system doesn't have noise in it when it's doing nothing. It's very common for us to be called into environments where people say, look, I've got this system, it's noisy, it's showing 120 millisecond spikes every once in a while. I need this to not do any worse than 10 milliseconds. Can you do that for me? And can we set an experiment up that'll show it? Now, we know we can get the Java application and the JVM to that level, but before we do the experiment, I ask people to run an idle J-Hiccup for a couple of hours on the system we're about to test on. And you'd be surprised how often the picture comes back like that. An idle system doing nothing is experiencing a 20 millisecond hiccup. And if that's going to happen, I'm going to fail my test no matter what. There's no point in doing the experiment because when it's doing nothing, it's already failing, right? So before we spend all our time for the next 2 weeks testing it and trying to improve it, we want to just clean the system and get this kind of result before we start the test. Just clean your workspace, clean your system, get it quiet. I think somebody here asked me questions about this before in the break, and this is a common thing we do. Just look at your system, and by the way, you could use this tool even if you're not running Java, because it doesn't depend on Java. This is just measuring the system behavior. And this is what we know you can get Linux to do. On the right side, that's a tuned Linux system. Getting Linux to have a noise level that's no bigger than about half a millisecond is very doable, as long as you're not running on a hypervisor and as long as people let you actually change things like power states and control the kernel settings. There's a current or recent discussion on the mechanical sympathy Google group that has some recommendations that I put up and other people put up for common initial settings. So anyway, you can get it that way, and I highly recommend that you spend your time on a system and clean it up before you do any other measurements. Because if the idle background noise is going to be bigger than your target, you're going to waste a lot of time if you start experimenting too early. Once you have what you believe is a clean system, you can start doing actual comparisons or actual measurements. This is a way to measure the same workload on different collectors in Hotspot. This is a 1 gigabyte cache inside an 8 gigabyte heap. It's an EH-cache test. It's actually an EH-cache benchmark. And you can see kind of the shapes for parallel GC versus the shapes for G1. It's just interesting shapes. And until I plotted this, I didn't realize that G1 has those interesting kind of decaying pause lengths, which no other collector I know of has. And I'm not sure exactly what the mechanism is, but it's there. And you can get some intuition